There is a very specific, very satisfying feeling when you sit down at a computer with a well-tuned desktop environment.
Oh, yeah.
Like you press a key and a menu just slides right down. Click an icon, a window snaps into place. There is no stutter,
No lag at all.
right? No lag. It feels solid, like a single machined block of aluminum.
It does, but it's
Okay.
really just the illusion of solidity.
The illusion.
Yeah, because underneath, as we know, it is definitely not a block of aluminum. It's a chaotic, swirling assembly of, well, libraries, assets, scripts, legacy code, new code, and they're all trying to talk to each other at the exact same millisecond.
That is a great way to put it. It's like a duck gliding on a pond, right?
Exactly.
Totally calm on top, but just paddling furiously underneath the water.
Furiously, yes.
And today, we are going to dismantle that illusion for you.
Oh.
We are putting on our hard hats and going way down into the engine room of the GMA desktop environment to see exactly what makes it tick.
It's a really fascinating deep dive today, because we're looking at the plumbing.
Software plumbing.
Right. And I don't use that word lightly.
Yeah.
Our source material today actually revolves around this whole concept of being a software plumber.
I love that imagery. We are drawing from a brand new technical blog post. It was published literally today, Sunday, February 22, 2026.
Fresh off the press.
Very fresh. It's by a developer named Ang over at qianmeng.org.
And the post is titled Notes on GNOME Application Development Part 2, How GNOME Shell Manages Extensions via GResource.
Which I know.
It sounds so dry.
It sounds like the driest cracker you have ever eaten in your life.
Notes on Development, GResource.
Exactly. But do not let that title fool you. This isn't just some textbook entry we're going over.
Not at all.
It is essentially a detective story.
It really is. It starts with a super simple Hello World extension and somehow ends up with reverse engineering a compiled binary just to find missing files that theoretically shouldn't even exist.
It's a mystery about where the code actually lives. And along the way, we're going to learn about the architectural decisions that keep our Linux desktops so fast.
So our mission today is basically threefold. First, we want to understand the basic file structure of a GNOME extension.
Okay.
Second, we want to solve that mystery of the missing file.
The detective part.
Right. And third, we really want to break down this clever piece of engineering called GResource.
Which is the secret sauce. It's the reason why GNOME apps don't just feel like a loose, fragile collection of scripts.
Exactly.
But before we get into the heavy binary lifting, I kind of want to start right where the author starts. Ang refers to himself as an old software plumber.
I really like that framing.
Me too.
Yeah.
And he opens this highly technical post with a bit of life advice that I think applies to anyone, whether you write code or not.
He talks about the capture it now philosophy.
Yeah, he talks about the friction of learning a new system. We have all been there.
Oh, absolutely.
You're reading documentation, you're totally confused, nothing makes sense, and then suddenly, click.
You finally understand how X connects to Y.
Right. And his point, and I found this really profound, his point is that the moment you understand it, that insight immediately starts to decay.
You forget that you ever found it confusing in the first place.
It's the curse of knowledge.
Exactly. Once you know something, it becomes obvious to you. You literally can't imagine not knowing it.
So Ang says, if you don't write down the note immediately, like that raw aha moment, you lose it. You have to capture exactly what was confusing and how you solved it right then and there.
Because if you wait, you can't write a good tutorial later. You've lost your beginner's mind.
I feel that so much. It's like trying to describe a dream 3 hours after you wake up. You just lose the texture of it.
You really do.
So Ang is taking these notes in real time, right now in 2026, as he bootstraps a GNOME extension.
Right.
So let's walk through that setup. If you want to build an extension for GNOME today, what does the system actually give you?
It's surprisingly minimal, honestly. The plumbing is very clean. When you run the creation command, GNOME generates a directory in your home folder. Specifically, it goes into the hidden folder .local/share/GNOME Shell/extensions.
The secret basement of the home directory.
Right, the hidden folders. And inside a folder with your extension's unique ID, you get what I call the holy trinity of files.
Just 3 files.
Just 3 to start. You get extension.js, metadata.json, and stylesheet.css.
Okay, that sounds exactly like a standard web stack.
It does.
You have your JavaScript for the logic, your JSON for data, and CSS for the visual style.
On the surface, yes. But the author actually points out a quick optimization right off the bat, a plumber's tip, if you will.
Oh.
That stylesheet.css file. You can just delete it.
Delete the boilerplate. Isn't that dangerous?
Not at all. If you aren't doing any custom styling, like if your extension just adds a functional behavior or a logic tweak, GNOME doesn't require the file to exist.
It just uses the standard system look.
Exactly.
I like that. It speaks to the architecture. Don't load what you don't need.
Keep the pipes clean. Minimalism is totally key to performance here.
Now, let's look at the metadata.json file. Usually I just gloss over metadata files because they are just paperwork.
Right, mostly standard info.
But there is a version number here that anchors us in time.
The shell version. In the source, it's explicitly listed as 49.
GNOME 49. We are officially living in the future.
We are. But actually, the most interesting packaging detail isn't the version number at all. It's inside the extension.js file itself.
Oh, the licensing header?
I was hoping you'd catch that.
Yeah, the boilerplate code, the code GNOME gives you automatically when you start defaults to GPL 2.0 or later.
Right.
So let's unpack this for the non-lawyers listening. Why is that specific number, version 2.0, noteworthy today?
Well, if you follow open source licensing, you know that GPL version 3 has been the standard for modern copyleft for a long time now.
Right.
It has way better protections against patent trolling. It handles tivization, which is hardware locking, much better.
So you might ask, why is a cutting-edge 2026 desktop environment defaulting to a license from the early 90s?
Exactly.
I just assumed it was legacy inertia, like they've always done it this way, so nobody bothered to update the template.
A lot of people assume that, but it's actually a very strategic play for something called upstreaming.
Upstreaming. That sounds like salmon swimming home.
It's really not far off. In the open source world, upstream is the main project.
Okay.
So let's say you write a killer extension. It fixes a bug, or it adds a feature that is so fundamentally essential, the core GNO team sees it and says, we want this.
We want this to be part of the default desktop for everyone.
Out of the box, yes.
That is the holy grail of development. Your code literally ships with the OS.
It is, but here is the catch. The core GNOME Shell codebase is licensed under GPL 2.0.
Ah.
So if you license your custom extension under GPL 3.0, those two licenses have compatibility friction.
Legal friction.
Right. You can't easily mix them in the same binary in certain directions without causing major legal headaches for the maintainers.
So by defaulting the template to 2.0, the system is essentially saying, hey, keep your options open. You might make the big leagues.
Precisely. It keeps the door propped open for your code to eventually graduate from being just an extension to becoming a core feature.
It's a subtle nudge towards ecosystem unity.
It really is.
That is a fascinating layer of legal plumbing, planning for success before you have even written a single line of actual code.
It's very smart engineering.
Okay, so the legal paperwork is done. Let's get to the technical mystery.
The detective story.
This is where it really kicks in. The author is looking at his extension.js file, specifically the import statements at the very top.
Line 18. The scene of the crime.
Line 18, I'll read it. It says, import extension from, and then in quotes, resource colon slash org slash gnome slash shell slash extensions slash extension.js.
Now, to a web developer, or really anyone who has written modern code, that looks vaguely familiar, but also just wrong.
It looks like a URL.
It does.
But it starts with resource colon slash slash. It's not HTTP, it's not file. And the path is org slash gnome slash shell.
Right. So naturally, the author thinks, okay, I want to see that file. I want to read the code inside extension.js at that specific path.
So he goes to his file system.
He does.
He opens his file manager, goes to the root directory, looks for a folder called org. And
it's not there.
It just doesn't exist.
It doesn't exist anywhere on the disk. And this is the disconnect. You have a line of code explicitly telling the interpreter, go get the code from this folder. But the folder is nowhere to be found in the directory tree.
So if I'm Ang, our old plumber, I'm getting pretty suspicious right about now.
Oh, yeah.
How does the computer know what org slash gnome slash shell is if I can't find it? Is it downloading it from the internet on the fly?
No, and that is the trick. He knows that GNOME Shell is a program running locally.
Right.
So he starts hunting to the binary. He drops into the terminal and uses the which command to find the executable.
Which points him to us daver slash bin slash gnome shell.
Right, but that is usually just the launcher. The real heavy lifting in Linux usually happens in shared libraries, those .so files.
Shared objects.
Yes.
For listeners who aren't Linux wizards, let's clarify that real quick. A .so file is basically the Linux equivalent of a Windows .so file, right?
Pretty much exactly. It stands for shared object. It's a blob of compiled code.
Right.
Instead of every single program rewriting the code for, say, draw a window, or handle a mouse click, they all just share these library files. Saves a ton of space and memory.
Okay, so Aang puts on his detective hat or his plumber's helmet and uses grep to look for libraries related to GNOME.
He's scanning the system folders.
And he finds a suspect.
He finds libshell-17.oso, located over in osr/lib/GNOME Shell.
Okay, so he's found a binary file, but this is where it gets tricky. You can't just open a .so file in a standard text editor.
No, you definitely can't.
If you try, it just looks like alien gibberish. It's machine code.
Usually, yes. But Aang has a hunch here.
What's his hunch?
He suspects that the missing file, that JavaScript file from the import path, is somehow trapped inside this binary.
Like a fly trapped in amber.
That is exactly it. So he uses a special tool. This isn't a standard Linux tool you'd use every day. It's specific to the GNOME toolkit.
Okay.
It's called GResource.
GResource.
And he runs a very specific command, GResource extract.
Extract. That sounds promising.
He points it at the binary file, libshell-17.so, and asks it to extract the specific path org/gnome/shell/extension/extension.js.
And what happens?
It works. It literally spits out the code.
Wow.
The full readable JavaScript source code was sitting right there, embedded entirely inside the compiled machine binary.
So the text file was inside the machine code file the whole time.
It was. And not just that one file either. The source material mentions a staggering number here.
Let's hear it.
That single binary file, libshell-17.aso, contains 159 different JavaScript files.
159.
Plus icons, plus UI definitions, plus other random assets. It is all packed in there.
Okay, let's pause right here, because this is the core concept we really need to understand today. This is GResource.
Yes, it is.
Why on earth would you take 159 perfectly good human-readable text files and bake them into a massive binary blob?
It seems messy, right?
It seems very messy. Why not just have a normal folder with the files sitting in it?
It seems messy to us humans, but to the computer, it is incredibly elegant.
How so?
This is all about architecture and performance. The blog post actually links to the official API documentation for GResource, and it highlights 3 main benefits for doing this.
Okay, let's go through them.
The first one is actually for the humans, ease of development.
Wait, how is baking files into a compiled binary easy for a developer?
Well, because the baking happens at the very end. As a developer, you don't actually work inside a binary file.
Ah.
You write your code in normal text files, organized in normal folders. You have your clean structure. The bundling only happens automatically when you click build.
So your daily workflow remains totally normal.
Exactly.
Okay, so it's easy for the coder, but what is the benefit for the user? For you or me, sitting at our desks just trying to open an app?
That brings us to the second, and arguably the biggest benefit, efficiency.
Efficiency.
Think about what happens when an application starts up. If GNOME Shell kept those 159 files as loose text files on your hard drive, every single time you boot it up, the system would have to perform 159 separate read operations.
I see. It has to ask the file system 159 times. Where is this file? Okay, open it. Okay, read it. Okay, close it.
Exactly. And even on a blazing fast SSD, there is overhead for that. There's latency. It's called I/O overhead.
Right.
By using GResource, the system loads one file, just libshell-17.so. It loads it straight into memory.
One single reoperation.
One read.
Okay.
And once that binary is sitting in your RAM, accessing any of those 159 scripts is virtually instant. The source describes it as acting like a mini cache drive.
That is a great visual. It's a virtual flash drive that lives purely in your computer's RAM.
Right. So when you hit that super key and the desktop overview slides in, the system isn't pausing to go read a script from your physical disk to figure out how to animate the window.
The script is already there.
It's preloaded right in the memory map of the application.
That perfectly explains the solidity we talked about at the start of the deep dive. That snappiness is literally engineered by eliminating disk access.
Speed is king.
Always.
But there is a third benefit the source mentions too. Simplicity and security.
Okay, security I get. It's obviously harder to tamper with a compiled binary, but simplicity.
Simplicity in deployment. Think about it. If you have an app with 200 loose files, it is very easy for one of them to get accidentally deleted or corrupted or moved by a user.
Oh, sure. Maybe you're cleaning up old files and you delete the wrong subfolder.
And then your whole desktop crashes because it can't find some random icon.png.
Right.
When you bundle everything into a single blob, it becomes atomic. You either have the whole app or you have nothing at all.
It eliminates an entire class of bugs related to missing assets. And on the security front.
Well, it's not encryption per se. You saw that Ang could extract the code plainly once he had the right tool,
Right.
but it strongly prevents casual tampering.
Because you can't just open a folder and inject a malicious script.
Right. You can't just change the behavior of the login screen by quickly editing a text file while nobody's looking. You would have to decompile, edit, and recompile the binary, or use really sophisticated memory injection tools.
It massively raises the barrier to entry for messing with the system.
Significantly, it keeps the whole environment predictable.
I want to circle back to that weird URL that started this whole investigation. The resource // syntax. Now that we understand GResource, that syntax makes total sense.
It does. It's a custom URI scheme.
Just like HTTP is for the web or file is for your hard drive.
Exactly.
Yeah.
But resource is completely specific to GJS, the GNOME JavaScript runtime.
Right.
When the runtime sees that specific prefix, it knows instantly. It says, don't look at the hard drive, do not go to the disk, look at the memory address where I loaded the bundle.
It's an instruction to look inward, not outward.
That is a beautiful way to put it. It's an internal lookup mechanism.
Which is so...
And it's important to note, standard JavaScript in a normal web browser like Chrome or Firefox would completely choke on this.
Because they don't know what resource means.
Right. If you put resource : / in a website's code, it would just fail. This is specialized plumbing built solely for the desktop environment.
You know, what I really love about this deep dive is that we started with a very generic how to make an extension post. We could have easily just stopped at, here are the 3 files you need.
A lot of tutorials do stop there.
Right. But simply by asking, where is that file? We uncovered this massive fundamental architectural decision regarding memory mapping and binary bundling.
It really shows that even in high-level languages like JavaScript, when you are dealing with an operating system, you eventually hit the metal.
You eventually have to care about how bytes are physically stored in memory.
You do.
It definitely gives me a lot more respect for the engineering team behind the scenes. It's not just making it look pretty, it's how do we make 159 separate scripts load in 10 milliseconds?
That is the real challenge. And Ang, our source, did a fantastic job of peeling back that exact layer.
He did. But I do have a lingering thought here, and it goes back to the old plumber persona we talked about. To find this out, to see how the system worked, he had to use grep. He had to use GResource extract.
Go on.
We love Linux and we love GNOME because they are open source.
Right.
The code is free. We can read it. We can learn from it.
Yes.
But GResource essentially seals the code inside a black box.
It does. It puts the code behind a glass wall.
Right. To read the code that runs my own desktop, I can't just casually browse a folder like I used to in the old days of simple scripts. I have to know about libshell-17.so. I have to know specific command line extraction tools.
It raises the barrier to curiosity.
Exactly. That's my provocative thought for everyone listening. If the goal of open source is to encourage people to tinker and learn, does this efficiency-driven architecture inherently hurt that goal?
It's the classic trade-off in computer science.
Performance versus accessibility.
Yes. We want the desktop to be fast, stable, and secure for the millions of users who just want to sit down and do their work.
And bundling achieves that.
It does. But for the one kid who wants to see how the overview animation actually works.
She has to bring a blowtorch to open the hood.
She does. The code is still legally open. The license says she can see it. But technically it's sealed shut.
It requires a level of technical sophistication just to access the source code that simply didn't exist in the days of plain interpreted files.
It's a move from transparent to translucent. You can see it, but you really have to work for it.
And maybe that's okay. Maybe that filtering process ensures that only people who really care, like Ang, our old plumber, get to mess with the internals.
It stops you from breaking things accidentally, that's for sure.
That's true. It protects us from ourselves.
It does. And it keeps our desktops feeling like that solid, unbreakable block of aluminum.
Well, that is certainly something to think about the next time you install an extension, and it just magically works. It works because of a lot of hidden pipes and valves.
Absolutely. The plumbing matters.
That is all for this deep dive into the hidden architecture of GNOME. A huge thanks to Ang at kiameng.org for the detective work today. And thanks to all of you for joining us as we extracted the truth from the binaries.
Always a pleasure to dig in.
We'll catch you on the next one.